That's right. Yeah. Oh no, you're right. Yeah, you're right. He was supposed to. Chris has that. Yeah.
Dylan McBride was in there.
Dylan was there?
Yeah. He turned it down.
Oh, so he wasn't there.
He wasn't at the event, but he was one of the people.
So we have a plane. Okay, we have a plane. And we have the magnetic field going through this plane, through this surface area. And the symbol for magnetic field is D. Okay, that's the symbol for magnetic field. Okay, so it's supposed to be a fancy B.
Can we just do regular B?
You can do a regular B.
Okay.
Okay, so obviously this is B here perpendicular, this is B here parallel. Okay, there's two lines there. So how do we define the magnetic field?
Dot product?
Dot product? Yes. Thank you for sharing. Actually, what we want to look at is here we have the magnetic field. Okay, magnetic field lines going through the area. The problem is they have a lot of different terms to define this stuff. And what we're going to look at first of all is what we term the magnetic flux. Okay. Does that word sound familiar at all?
No.
You've never heard the word flux before?
No.
Yeah.
Oh, you put it on the solder.
I mean, I'll take a Gauss.
I'll take a Gauss. Okay, so
Oh boy.
the symbol for magnetic
Waiting
flux
way too long to drop that.
is
An entire unit to drop that.
remember we had electrical flux? Remember that?
I've suppressed those memories.
Nobody remembers that? Okay. Now we have magnetic flux. Now magnetic flux, depending on the textbook, will be the little TIE fighter symbol there with either subscript B or subscript N, and for magnetic or B for that. I'm going to use B. Some textbooks use M. So magnetic flux is the symbol. Okay. And magnetic flux, by definition, is right? Okay. The number of field lines or magnetic field lines which is B, passing normally through a surface area. Passing normally through a surface area. Everything good? Yes, no, maybe? So we're looking at that's passing normally through the area, correct?
I didn't know these.
It's going to be a fun 8 weeks, I can see it. Okay. Now, John suggested what?
A dot product.
He said a dot product. He didn't say a cross product. Okay. What do you think the calculus formula should be here, since you know Gauss?
The surface integral for EDA.
I was gonna say
BDA. Shit.
I was gonna say that as a joke, but it was right.
It's not a joke. Okay, the surface integral.
Look at Nico.
of
I'm on fire.
Which, because it's a dot product, equals what?
B cosine theta
BA cosine theta. Okay, and some textbooks will actually put the little perpendicular symbol in there because we're looking at it crossing normally to a surface. Okay. So, if theta equals 90, what does that tell you? are there any magnetic field lines
No.
penetrating the surface?
No.
Now, if theta equals 0,
Yeah.
okay, it would be a maximum. Any angle in between, it's an angle in between, okay? Now, what are the units for this? I don't know if anybody knows. Anybody know what the units are? Hmm?
Voltmeters.
For magnetic flux.
Yeah.
It can be.
Magnemeter squared.
Magnemeter
Magnemeter squared.
Magneto, yes, it's magneto. Yes. Oh, my lord. Okay.
Webers.
Well, let's go with this. Named after the guy who was into electricity.
Maniglia.
Yes, these are Meniglias, yes.
Yeah, got it.
Tesla.
Ooh.
Okay.
Cool sign name.
Teslas. It's gonna be a long.
It's gonna be long. Okay. Let's see if we can guess what the units are for magnetic flux.
Jared, it's because it's attractive.
Ah,
Shut up.
Got I'm on fire.
So, a Tesla,
think.
What do we think?
Tesla meter squared.
Why am I
Using
doing
units.
What notes can I skip here? I'm trying to figure out.
Dimensional analysis is complete. It's going to be a Tesla meter squared.
Huh?
It's not.
What is it?
Tesla meter squared.
Yes, what's the name for it?
A Weber.
A Weber, thank you.
Oh.
Don't they make root beer? A drive-in root
Should be a
beer
war.
What?
It is a board.
Yeah,
It's a Weber.
I'm pretty sure, and they got the spinny thing.
How are you supposed to know?
Look it up.
What did you say it was?
Someone has to remember.
Tesla meter squared.
I got that
Jason
right.
didn't know it all is lost.
Okay, Tesla meter squared. Okay. So we have a Weber and a Tesla meter squared. Named after the guy Weber.
Oh, okay.
Why is it called Tesla meter squared?
I'm waiting for a quarter to show up.
You want a Corbin to show us?
Yeah, that way it knows.
Yeah, we're not gonna go there. Okay. So,
With the Corbett.
A cubit. Okay.
Carter brilliantly yelled out. Brilliantly yelled out.
Like music's my ear.
What did you give me for the formula for electric flux, Carter?
EDA? Or the
Surface
surface
integral
integral EDA?
EDA.
Equals Q over
That's what you asked. Equals?
Q over F.
Q or what? Yeah. Epsilon sub 0. Now, somebody put that into words.
The
Gauss's law. Put it into
electric
words.
flux through a surface is equal to the surface integral of the electric field times the
All right, well, you're giving me the.
equals the charge enclosed over the permittivity constant.
Okay, try. I wanted to try. Okay. So the electric flux. You already had this. So you should. So you're saying that the electric flux. Or another way of saying it is the net number of lines.
Is proportional to charge enclosed.
You can say either is directly proportional or is numerically equal, however you want to say it. You had this, correct? This is Gauss's law. That the electric flux and the net number of lines crossing a closed surface is numerically equal to the magnitude of the enclosed charge. In simplest terms. Yes, no, maybe?
Yes.
Okay. What else do you know if I were to draw, if I were to put a charge Q here, and you draw a Gaussian surface, the field lines that are positive are coming out, going through that Gaussian surface. Okay? You also know if I have a positive charge and a positive charge, or a positive charge and a negative charge, that a field line does what? You have a positive and negative charge. The side never crossing, what else about it?
Goes from the positive to the negative.
It goes to positive and to the negative. So the electric field lines, okay, the field lines originate on positive Q and terminate on negative Q. That should all be reviewed, okay? Now we have Gauss's law for magnetism. Okay? Which is written right up there. And I'm going to ask one person in here, because we were having a discussion of this at the end of class yesterday. Okay? What does this equal? 0. Okay? Joe blurted out yesterday at the end of class, some of you didn't hear, that this equals 0. Okay? Okay. Joe, you want to favor everybody with your explanation of why it does not follow this logic?
Sure, because when you have a magnet, there's the with the magnetic field lines go from the positive end to the negative end always, and they don't go anywhere else. So if you take a Gaussian surface and you plot around anything, there's always going to be a positive end and negative end. So they're always going to fall. They're never just going to penetrate the surface. It's the other side.
It's not gonna go anywhere.
Did everybody hear that?
Yeah.
Okay. Okay. That's why it equals 0. Okay. Visually, I'll draw a little bar magnet here. What Joe is saying, if you have a north and a south pole, okay, that looks like a W. We have a west and a south pole, my new magnet. It's my new magnet, it's a west and a south pole. Okay, so you have the magnetic field lines are actually doing this. Okay, but what you don't see with a magnet, they're actually doing this. We're actually going through the magnet. So unlike field lines for electricity, these field lines form closed loops. So there is no origin and termination. So if you put a Gaussian surface around this magnet, as Joe was saying, the number of field lines going in and out are always equal to each other. So the net is 0, no matter where you put that Gaussian surface. Okay. The problem is people erroneously make this translation over. That's not correct. So it always equals 0. Okay. So for, I'll just put that in. The magnetic flux always equals 0 through a closed surface.
So, does that make the unit, the Weber, essentially useless? Because we're never going to have anything that's not 0 Webers?
In a closed circuit.
Yeah, because you don't have to always look at a Gaussian closed surface.
Well, we got to look at it through a surface area.
Yeah, but we don't have to look at it through a Gaussian surface. Let's put a closed surface now. We can calculate the
You don't think
magnetic
encompass the
flux.
whole object.
Alright.
This term actually, this
They just like that. We just do the calculation.
Until we get older. That's how.
everybody's going like, what do you have to calculate? This is the magnetic field. D is the magnetic field. Anybody got to guess what other term they use for that? Unfortunately,
Where you
look at the words on the board. You should be able to take a guess.
What?
This is called magnetic field, or
just do another.
Why would we do that?
magnetic flux. Number of field lines crossing closed surface. a lot of them. Thank you. Density?
Oh, yeah, the word.
I see dead people.
Oh, no. Not
Do I want to do anything else with this? Not really. I'm gonna go home.
Amen.
And I should get to the math. Okay. Everybody go with magnetism? What are you gonna do with this? Nothing. Nothing right now. You know, come into play later, because you can have a magnetic flux with a magnetic Gauss's law, but you can also have an Amperian surface as an Amps law. So we'll be getting to that a little bit later. I know you're so excited.
Really.
I know. Oh, God, please make this more interesting. I'm looking at the notes, but I'm trying to make this faster. Thank you. Think about it, I spent 2 whole days working with stuff at home during the Easter break. All right, we got a magnetic field. We got a particle in the magnetic field. Why would we put a particle in a magnetic field?
Because you're making us.
No,
A railgun.
no, why do we put particles in fields?
See,
We can't help it.
Make trees.
The strength of
To detect the field.
Yeah,
Okay,
Physics.
yeah, thank you.
yay! So I have a magnetic field. I put a charged particle in it. Positive charged particle. How are you going to notice if there's a magnetic field there?
It's gonna do something.
Hopefully. Otherwise, no. It'll move. Yeah.
No, magnetic field.
I have it, okay.
No.
We're gonna have to go to let's pretend. Okay. We have a magnetic field between Joe and Jason here. I'm a particle. Here I am. Is there a magnetic field between them?
Well.
You just said there was, didn't you?
How?
If it goes one direction.
One direction.
They broke up, so I guess.
Yeah, we can't really do this. Okay, can you tell? Is there a magnetic field?
No, you have to move.
Huh?
You have to move.
I have to move.
That's what you.
What happens if I do this?
Yeah.
No, you can't perpendicular.
Why?
I have no idea.
Because you gotta do the right hand roll.
Damn you. We're not getting to that yet. Okay. He's reading this off. Why is this not good?
Because you're moving along the field lines.
I'm moving along the field line, so I have to move at some angle that's not parallel to the field lines, okay? So the only way you can detect if there's a magnetic force and a charge, the charge is gonna be moving. If it's stationary or moving parallel to the field, you can't detect it. Do I have to actually write that down?
Yeah.
Really?
Yeah.
Oh, God.
Now I have to write it down.
What's going on?
So in fact, you rewrite over there.
Yeah, exactly.
Yeah.
So that's how you usually
Pretty damn, we have to start writing down this stuff. Oh, Lord. So, I'm gonna put a magnetic field. And we're gonna take a charge Q, positive charge Q. Did you have this last year?
No, I was gonna go ahead and say that.
Is that what you would have?
I had this on the SAT2 at blue.
And it's gonna move at a velocity v at an angle theta. Okay? Okay.
Wow.
Is this gonna experience a force?
It should.
It should. Okay? Well, the formula for it, and the only way you get the formula for this is by experimentation. There's no calculus derivation for it. B is F equals the value of the charge, velocity. You gotta put something between the B and the B.
QVC.
No.
Not times.
Cross.
Cross. It's a cross product.
Did you do the cross product?
Okay? Which is QBB what?
Sine.
Speaking Yiddish.
Okay. It's a cross product. Okay? Because it's a cross product, it follows what, Alex? Right hand rule. We're following right hand rule 1. RHR 1. That's the way they abbreviate it. RHR 1. Okay, so
Sounds like some kind of compound.
there's several ways you can do this. Okay?
Born under skinny.
Use your, do I have to go through this or you all know this?
No, I would do it because there's two of them.
Okay. Taking your right hand, okay, this is the way the textbooks do it. You should be taking and moving your hand so your hand curls to the smallest angle between B and B. To me, that's, can get very confused. I do it like this. Put your palm in the, this is an alternate. Put your palm in the direction of B and your fingers in the direction of B. Your thumb will go in the direction of the force. So where's your thumb going?
Into the board.
Into the board, okay? So this particular example, the force experienced by this thing is in. And what little symbol do we use for that?
A dot. No, an X.
An X.
There you go. Yeah. If we do a
That's
cross
in.
point into the paper, a dot
That's
is coming
in.
out.
You didn't know that? That's
Yeah.
the symbol for
Imagine
in.
if you were
Okay.
shooting an arrow.
That's
So if you're
in.
looking at it from behind, you see the
That's
fletching. If
out.
you're looking at it from the front, you see the point.
In case you didn't know. That's in, that's out. Everybody good with right hand rule? What happens if it's a negative charge?
Yeah, did you use your left hand?
If it's negative,
If it's
then
an
it's
electron,
negative and
you
it's
use
coming
your
out of the
left
board.
Yeah,
I'm
well,
pretty sure.
yeah,
I'm
well, yeah,
almost
we'll actually use your
positive.
right hand and it just reverse the answer.
But you could
You
use
could use your left
I'm
hand.
just saying. it's
You could use your left hand.
Y'all
Okay.
laugh.
I just find, I don't know, my left hand wouldn't,
I mean, it works.
That does, it works.
It does work. I mean, it does work, it's just, you look kind of weird.
You got like both hands going down. Starting to fire on.
Okay, everybody good? Let's look at an example of this. Okay, an example problem of this. And again, most of these examples are plug and play examples. So,
Calculator time.
except this one.
Yeah.
Of course. It wouldn't be sporty otherwise.
You should be able to get it.
Put your palm in the direction of the lawn.
.6 times 10 to the negative 19. 1.9 times 10?
1.6.
1.6 times 10 to the negative 19. I can't see.
By the way, is this a vector or scalar quantity? Vector, right? Cross product vector.
Force vector.
Anybody got the answer here?
Yeah.
Anybody know what you would do? Huh? Wait, what's the mass of proton? 1.67 times 10 to the negative 27. I'll give it to you in the test, because I doubt you remember that. If anybody needs the mass for protons, 1.67 times 10 to the negative 27 kilograms. The fact that Alex asked me that question means I know where we're going with this. Okay, so how would you get this answer? John's looking at it like he's just had a stroke.
F equals MA.
Yeah.
Well, yeah, F equals MA, so A equals F over M, okay? And what are you gonna plug in for F?
QVB sine theta.
QBB sine theta. So it's gonna be QBB sine theta over M. Okay, so we play plug and play. It is a proton, and the charge of a proton is 1.6 times 10 to the negative 19 coulombs. Okay, the velocity is 300 meters per second. V is 0.5 Tesla. The angle is 30 degrees. And the mass I just gave you was 1.67 times 10 to the negative 27 kilograms. Okay. And somebody calculate a Ouija board or Abaci.
7.2 times 10 to the 9
That's what I got, so we were both right.
gigameters per second squared.
Right, 7.2 times 10 to the 9 meters per second squared. That puppy is moving. As it should be. That number bother anybody? That speed bother anybody?
It's an acceleration, so it's not going to be going that fast.
Is it accelerating in the direction of the field?
Yes. Does the acceleration bother you that it's going that fast?
A little bit.
Really?
Well, it's accelerating at more than the speed of light per second.
Yeah, well. Nicola,
So it's not going at that acceleration for very long at all.
for anybody?
That's about it. Let's see what I can know at the bottom. We're gonna change to 2.67.
We're gonna have it work. Well, if it's active, it has to work. Okay. Okay. Park. I'm gonna have that tattoo.
You should have, yeah, just have this symbol, the park symbol on your shirt.
This morning was absolutely insane. I think every kid taking the test decided to make it. Well, we're gonna start trying to follow the directions this morning. One kid logged in, and I'm looking, so I can see what everybody's doing on my screen. One kid logged in, like, the teacher's calling me up. It's not working. I says, according to this, the kid just completed the test. He says, how's that possible? They just logged in. I says, obviously, they clicked every damn button and clicked complete. Oh, okay. Our scores are gonna be wonderful. RB is gonna be ranked 380th in the state out of 360 schools.
Make up schools.
They're gonna make a scale for this school. It's gonna be unbelievable.
Invent a new creature.
Yeah, it'll be definitely a new breed. Now, kids,
It's just flop on the keyboard, get better score.
here we go. Now you have a magnetic field. Can you have any other fields?
Yeah.
Electric, you can have electric and a magnetic field.
Gravitational.
Where do you see an electric and magnetic field, folks?
And electromagnetic.
Electromagnet, where else in this
A
room?
Hellman's
is
coil.
Electromagnetism.
Hellman's coil.
Beside a Hellman's coil. Anybody else see
TV.
electromagnetism?
Like,
Thank you, light. Light is an electromagnetic wave. Hopefully you're all seeing it.
you kept looking up that.
Yeah, well, thank you, that was a clue.
I was like,
Okay.
yeah.
Now,
Oh, Hellman.
Don't they make mayonnaise? Hellman's mayo?
That's how they need you.
okay.
His expression. Nothing.
I want to get rid of you.
Now, yeah.
He was like, that's a good idea.
Can you see it? You see the blue beam?
Yeah.
If you can't, you can get on.